So, maybe you heard about polarization. That goes back to the idea that term was coined in the late Middle Ages. And it's a term that kind of displays the fear of emptiness. And in the more modern times, it was, for example, Otto von Guericke here with this half spheres experiment, pumping out the air in Magdeburg, Germany, to demonstrate that there could be something like a region void of matter. And so, as we talk about the physical vacuum, okay, we can think about some sort of definition like Maxwell did. What is left when all that can be removed has been removed? So something like this, and an empty vessel or region of space. But it didn't take so long, and then until with Heisenberg and uncertainty, the vacuum was kind of filling up again with the non-zero ground state of the electromagnetic field modes, and also virtual particles. So we have here virtual particles and electromagnetic field ground states in our modern vacuum, or what we call the quantum vacuum today. And so this quantum vacuum, as you know, is associated already with a number of effects like lamp shift and anomalous magnetic moments and Casimir force, although sometimes disputed. There might be other interpretations of Casimir force also. But what I want to talk about here is properties of the quantum vacuum in the presence of external fields. So in particular electric or magnetic fields, which can serve to study the properties of the quantum vacuum with a light beam. And so this will be the main topic of this talk. And in particular, we will see there's a question if maybe the refractive index for the light propagating might deviate if we have external fields. Okay, going back just a bit, this question is quite old in principle. So already as early as 1898, there's an experiment from Morley and Miller, experiments on the velocity of light in a magnetic field. So these were differently motivated, and the magnetic field was along the arms of a Michelson interferometer, and the propagation of light was studied in matter. So kind of different questions, but already around 30 years later, we have experiments, the effect of a transverse magnetic field on the propagation of light in vacuum. So at that time, the question was around as well. And here we have an upper limit for the change of refractive index in vacuum of something like 4 times 10 to minus 7. So as we will see, this is about 16 orders of magnitude away from what we will be talking about later. Then a little bit later, in the 30s, when the positron was invented or proposed by Dirac, just a few years later, here's a paper from Heisenberg and Euler, which starts in the abstract with a nice sentence. According to Dirac's theory of the positron, an electromagnetic field tends to create pairs of particles, which leads to a change of Maxwell's equations in the vacuum. And so this is what they calculate here. So this would be the classical Lagrangian for the electromagnetic field. Then they calculate an extension, Heisenberg-Euler extension, which is here, so which is mainly quadratic in its components, and has a coupling constant, which is fairly small. So the nonlinear correction to the Maxwell equations coming from virtual pair production. And so today we have this QBD prediction that the light slows down in vacuum in the presence of a magnetic field. Right? As I said, it could also be an electric field. In the following, we'll only be talking about magnetic fields, because to get the equivalent of a 1 Tesla magnetic field, you would need something like 300 megavolts per meter electric field. So technically speaking, if there's any chance at all, it would be easier with magnetic fields to see such an effect. So the prediction, in fact, is that we have a light beam or a laser beam, for example, in the x-axis, which is linearly polarized vertically, and we have a magnetic field in the same direction, then the refractive index will change by this number, 9.3 times 10 to minus 24 times the magnetic field square in Tesla. So pretty small. And a different number comes out for the perpendicular direction. So if there's a right angle between the external E field and the light polarization, then the number is somewhat smaller, 5 times 10 to minus 24. And so as a result of this, this is what makes the vacuum birefringent. But it's important to note that these effects alone could be measured in principle, of course. So if you have any device that is phase sensitive, of course you can try to measure this effect alone or this effect alone. But yeah, looking at the difference between the two directions, so the vacuum is birefringent, which is of course nothing else than that the refractive index is different for different directions. And so we'll get back both to these. I will be speaking about experiments that try to see this effect, but later on we will also see that it might be possible to only see the single direction effect. Okay, in Europe, as you may know, you can make very nice train trips. So I recently went to the Alps to visit one of these experiments in Italy. And while I was on the train, I thought, okay, there is this interaction of light with the virtual particles and an external field, which slows down the light. But if there's no external field, then do the virtual particles also slow down the light? Why could this not be also the case? And so I asked my colleagues over there, and they said yes. And I was quite surprised by this. So in this picture, so you may take this as one possible picture of light propagation in QED. The propagation of a photon could be kind of split up. So the real photon propagation would consist of a bare photon propagation, which could travel maybe at an infinite speed or some speed faster than c. But then all the interactions with the virtual pairs would slow down the light. And as a result, what you get is the actually observed C, which is all familiar to us. And then the picture would just change a little bit. If you have an external field, then these virtual pair interactions just change and give you a little bit more phase shift, and then C depends on the external field. And yeah, I kind of find this idea surprising, but in fact there's a paper which is only 2 years old, which takes exactly this idea. So we show that the vacuum permeability μ0 and permittivity ε0 may originate from the magnetization and the polarization of continuously appearing and disappearing fermion pairs. And so they make some calculation about ε0 and μ0, and of course then as a consequence, because C directly relates to these also, they try to explain C out of the properties of the quantum vacuum. So that's a little bit of a side remark at this point, which I found interesting. Okay, so
how different is it if you neglect phase production? How different C will be?
That's a big question. That's a good question. In the paper, they speculate it might be infinite.
So it's slowed down because of action.
And as a result, of course, because it's a finite number of interactions, you also get a noise on the propagation on the speed of light. And so they make a proposal to make an experiment to measure this kind of noise. Okay, so QED is in some domains, as you know, very well tested to very high precision, but it's not very good tested in the weak field or low energy limit. So low energy means small against the rest mass of the electron, and weak fields is a field smaller, much smaller than the field you would need to produce pairs of matter, for example. So, but some people are trying hard, and I will show you now the dominant experiment, which is trying to measure the birefringence of the vacuum. And all these experiments are based on the ellipsometer method, which was proposed by Sabatini and Jacopini in 1979, after they realized how hard it would be to measure the direct refractive index of the vacuum. So they had the idea just to measure the difference in the vertical and horizontal direction with an ellipsometer. So all this is a well-polarized laser beam, the input, and then a Fabry-Perot cavity to increase the interaction length, and a magnetic field across this beam. And now there are two possibilities how you can modulate this field. So of course normally you want to modulate it to have some sort of measurable effect other than DC. And you can modulate it by either rotating the field around the beam axis, which would give you sometimes more phase delay in the stronger direction where the effect is larger, and sometimes in the direction where the effect is not so large. And by this you get a very small circular polarization component on the light. So the light coming out of the cavity gets very slightly elliptically modulated by this action. And the other possibility is very similar. You would set the field under 45 degrees, the B field, to the laser polarization, and then amplitude modulate the B field. This is the other possibility, and we'll get back to that. And all that this is then a detector for the ellipticity of the beam. In fact, it's a heterodyne technique in most cases, so you have another ellipticity modulator, which makes a large amplitude signal, and then some analyzer. And you cross out the linear part or block out the linear part and then see what is transmitted. It's quite similar to what, as if we would be in a microscope interferometer, we would phase modulate one arm and then would have heterodyne. Okay, and so as I said, the main experiment associated with this is called PVLAS, and people worked for 16 years on this experiment. The principal setup is just as before. It's a laser and then a vertical Fabry-Perot cavity and a superconducting magnet with a static field in the magnet, and the magnet is rotated around the beam axis and then beat out, as I explained. And after 16 years of work, the result was they could set an upper limit on the effect, which was factor 5,000 away from the prediction. And it was mainly limited by systematic error. So one big problem was stray fields from the magnet, which interacted with the mirrors, for example. So you can induce birefringence there also by magnetic field. So it's a hard experiment, and it's also a pretty large experiment. And this was discontinued in 2008, and then people thought about a new setup. So maybe the son of Sabatini took this over as a PI of this new experiment, which just started operation, and that's built on one single granite table, which is vibration isolated. And again, we just have a laser and very high finesse Fabry-Perot cavities around 3 meters long with a finesse of 700,000. Quite impressive. And then 2 dipole magnets. I will explain later how these magnets work. You can see them here, these blue cylinders, and they are rotating around the beam axis. Okay, this is a rendering of this optics table. It's pretty well made. So the table is isolated here, and the magnets, which weigh 400 kilograms each, are completely isolated from this structure to avoid vibrations which could couple into the signal. So here you see an image of the spinning magnet. Here's the ball bearing, and this is the outer holding structure. Here's the tube. It's a glass tube, so it should be non-magnetic as far as possible. Here's some black paint against scattered light. And there are other measures against scattered light. That's not so much different from our experiment. So in there are staggered baffles, such that if you look inside, you can never see the beam tube wall, for example. This is the PI of the experiment. And here's the latest result, which is quite impressive because it improved over the old results by a factor of 100. So we have here the time axis. EFRT was an early experiment in the Brookhaven lab in the US, so which was a factor 40,000 away maybe. And then you can see how these, this is the old PVLAS experiment. This is a new test setup for this experiment. And EMP I will talk about in a moment. Other groups have tried but have stopped again. So in 2006 there was one paper from the PVLAS collaboration where they said they saw an effect which they could not explain, and then people speculated if this could be a sign for axion particles, and so at that time new experimental proposals came up, but after a while most of them saw how hard it is. Well, this is my interpretation, but so at the moment only this PVLAS is left, and this one other experiment. So now they are just at the end of last year they came close to a factor of 10 to 50. And so currently it's limited by unexplained noise, and one suspect is, for example, birefringence of
So those 2 points don't look like upper limits, they're measurements with error bars that exclude QED.
I think these error bars, I don't know, just mean the confidence on that upper limit, on that noise level. That's how
Okay.
that makes sense.
Right, they're not claiming that it's
no. It is upper limits, and I think yes, the error bar just pertains. It's just noise. They just measure noise. Okay, and that was PVLAS, and just a few words about the experiment BMB. And they don't rotate the magnetic field around the laser beam axis, but they make a time modulation of the field with pulse magnets. And
what's the frequency of this rotation?
That 3.75 hertz, and then the signal is at the square frequency, so 7.5. And so they do amplitude modulation, and the idea is that, as we will see also in a moment, that if you do a large field for a short time, you can save in overall integration time. So that's the idea of pulse magnets, but it's also a very hard business, so they also found systematic problems, and they also redesigned the complete setup, so they have a new setup now, which is fairly young, as you see, and the principle is the same. We have some interaction region within a cavity, and this is the pulse magnet. So the essential feature of this is that you have a current running next to the beam tube, which makes a vertical field in the middle of the tube. But these pulse coils run in cryostats. So typically you make one pulse, and then the thing heats up from liquid nitrogen temperature to room temperature, and then cools down again over 1 hour, and then after 1 hour you can do the next pulse. It's quite terrible. Okay, to summarize this part, these experiments, PVLAS, BMP, and others, they measure a polarization variation of a laser beam induced by a varying magnetic field, and this can be, as I said, modulation can be spatial or temporal. And the typical problem is birefringence of mirror optics, for example, and the best upper limit is factor 10 to 50 away from QED prediction. Okay, now we slowly move to gravitational wave detectors and phase-sensitive interferometers. So if we arrange these techniques, rotating the B field around the axis and modulate the strength of the field in the matrix with the measurement of polarization, as we have been talking about so far, or the possibility now to maybe measure the phase of the light directly as it propagates to vacuum. And so, yeah, this is what these experiments have been doing, measure polarization. But yeah, we are working on phase-sensitive devices, so could gravitational wave detectors maybe be used used for this kind of measurement. And there will be two possibilities. Again, rotate the B field around one arm of the interferometer, for example, which would make a phase modulation according to this difference between the two directions. So this would measure the birefringence of the vacuum. But if we could amplitude modulate the field, we could get these two indices, horizontal or parallel and perpendicular independently. And this also has some implications for particle physics. So I have mentioned axions, and there is a connection to particle physics, mainly with respect to milli-charged particles. So these are hypothetical particles with some mass and charge smaller than the electron. And so if these fermion pairs make up the quantum vacuum, then of course these particles would do this as well and make an additional signal on top of the standard electron expected signal. And so these would show up as an ellipticity, just like the electrons do, the virtual electrons. And another class of particles, axions, as they have been first proposed to explain CP violation or CP symmetry. And so if it would be the case that the light photons would couple to axions, then that would mean some photons would disappear in this process, and this is equivalent to some absorption, which would be more in one direction than in the other direction. And so this would be corresponding to some polarization rotation. Okay, but this is just a side remark. People sometimes use this to motivate this QED measurements beyond the standard numbers that it has in it. Potentially it has this connection to particle physics.
What do you mean by frozen? You would see a different phase shift for the wavelengths as well?
Yeah, in this context, I think people just use it to say that in one direction you would have more absorption than in the other direction.
For polarization?
Yes, for polarization. Okay, so just a few slides. So this idea is not new to use interferometers or gravitational wave detectors for this kind of measurement. So there are a few papers. One of the first ones from 1979. So that was the time when interferometers were also regarded to be useful for gravitational wave detectors already, or just a little bit later. And so in this paper, they proposed some sort of Michelson interferometer, maybe with delay line, but they already point out that it would be another setup, any similar setup like this. And at the time, they had 30 milliwatt lasers, and they boldly extrapolated to 30 watt lasers, which seems quite fine today, of course. And so the numbers look about right there. So they concluded it could be done, but it's not easy and so on. But gravitational wave interferometers, because there's this interest in interferometers, might drive it forward in the end. In 2002, then there's what I saw the first discrete mention that gravitational wave detectors as LIGO or GEO could be used for this kind of purpose, but it's kind of too optimistic in assuming that the sensitivity can be increased in the future as a function of the finesse. I think it comes from a picture where people think of multiple bounces like in the other experiments. And it also does not make use of integration time, so that goes to the other side, this effect. And then there's a pretty good paper from 2009 by Sabatini, also this PI of the PVLAS experiment, and our colleague Enrico Caloni, and they mainly point out the new physics potential with respect to milli-charged particles and axions as a motivation for this kind of experiment. And they do some simple calculations if it could be done at Virgo, in particular how large does the field have to be and how long would the integration time be. And around the same time, there came out a paper that looks at the possibility for LIGO and GEO to use pulse magnets. So this is now the idea to do amplitude modulation of a magnetic field across a beam tube, and do it with this method. And they they conclude it should be well doable. However, they assume apertures of order 1 centimeter. So, and that's mainly motivated by the fact that pulse magnets exist for a clear aperture of order 1 centimeter, but they do not exist yet for larger apertures. So as we will see, this is a main problem for using pulse magnets. And so then mainly what I did in this paper, which just recently came out, which was kind of missing in all of the other papers, is to look, is it really feasible from our practical perspective of the interferometer, and mainly looking at possible magnet design, because that was not done by anybody before. So can we build such a magnet to make such a measurement feasible?
I have a question.
Yes.
When people do the calculations for when they're interacting with particle and anti-particle pairs, does anybody put in specific things like TT bar or CC bar or BB bar?
They're all much, much smaller. They're all much, much smaller. It goes like 1 over the mass of the virtual part. Vacuum polarization.
Oh, so you're saying that the lower mass is effect.
So lower the mass. That's why you talk about just electrons. It's not mentioning muons. The other thing that I always like to remind people of is, if you look at that diagram, you've got the propagating light in the vacuum, and you got the virtual vacuum polarization, and dot, dot, dot. And you say, the first term maybe is infinity, the next term is minus infinity plus the speed of light, and so on. You're doing perturbation theory, because that's the only way we know to do quantum electrodynamics. But nature doesn't do perturbation. So this is our picture of what's going on. But it's not really what's going on. What's really going on is more complicated than that. And it's too simple to think of it as just interacting with vacuum. It flows.
Yeah, I easily believe that. Yes.
We don't know how to think of it better because we don't know how to do these calculations non-perturbative.
Yeah.
But string theorists do. So they have a completely different picture.
Okay, so going to the question of, is it feasible for a gravitational wave detector? What is at the basis of this, of course, something like the probably well-known formula, how much you have to integrate to detect a sine wave in noise. And so we have noise amplitude, spectral density for displacement, and some displacement signal that, as you know, the integration time for some given SNR, so 1 in this case, goes with the square of this ratio. And so as the spectral density, we will put in here the displacement spectral density of our detectors, and as the signal, we will have this, what I said earlier, this 9 times 10 to minus 24 times E squared times E. So the important thing to maximize in our setup is a magnetic field square times the interaction length. So the excitation, I would call it, which makes our signal is proportional to E squared and the length. So this is the quantity to maximize in any setup. And so at the core of this, what this formula yields is a graph of integration time for some given displacement sensitivity over here. So in the middle is 10 to minus 20 meters per square root of hertz at any frequency of your choice, where your detector is more sensitive and where you can modulate the magnetic field. And integration time for an SNR of 1 in years. So conveniently, so here is 1 year. And I put an arrow here for what we think we can do with advanced detectors in the next few years, like 10 to minus 20 meters per square root of hertz. And then there's a set of 3 excitations, 1, 4, and 16 Tesla square meters, and a set of two lines for the 2 modulation systems. Either you rotate the field around the axis, or you amplitude modulate it, which is a bit harder, as we will see. And so, to look at this ballpark, we have 2 times 10 to minus 20 and something of the order of the middle 4 to 10 Tesla square meter, so we end up here in a month integration time. So and then it depends on what SNI you want.
So
This is for one sigma effect or something?
Yes, exactly.
this is at the
SNR
QCD.
one.
This is at the QCD prediction.
Yes, this is the QED prediction, so
Yeah,
without any
QED.
extra particles. Right. And so, yeah, I mean, integration time of a year is possible. And that's a nice thing on the gravitational wave detector. You get it for free, kind of, because the detector runs anyway. You can integrate well. But if you have systematic errors and you have to do it again 1 year and again 1 year, then it gets kind of troublesome. So something like a month seems a good number to aim at, then at least as a start. And so that would be something like 4 Tesla square meter, or this sensitivity 10 Tesla square meters. And what I did first to start with is to calculate magnets for 1 Tesla square meter, as we'll see. So just as a reminder, these are our familiar displacement sensitivities for the detectors, which are, we think, will be achieving this over the next years, and dash line for hypothetical detectors. So this is a kind of a wordplay. This is QHF upgrade is an upgrade to the QHF program. So this does not exist yet. This kind of upgrade. It's a displacement optimized upgrade, which we thought about just for this purpose, but it's still very hard. And yeah, this would be an advanced live upgrade and ET.
So this is an upgrade which would make room for one of these magnets.
Yes, exactly. It would remove the folding of the arms and to make you only displacement sensitive. Or I mean the gravitational wave, but you sacrifice the factor.
But the D there, the D in your formula is
Yes.
the length scale of the magnetic field,
Yes.
and that's about a meter is what you're
Hmm?
It's about a meter is what you're assuming.
It doesn't matter. What matters is this B squared times D. How you make it is to your choice.
You're going to tell us how you think what you're...
Yes.
I don't want to think you're going to get to the punchline, but you said it yourself. Even Tesla scale fields, it's hard to get Bohr sizes.
It's possible. Okay, so yeah, exactly going to this question, is it possible? Because the first question is how large does it have to be? Because the energy, as you point out, in a magnetic field goes with the square of the B field and with the square of the size. And this is why it's hard to make large and strong magnets in the first place. And so we would have to ask, how large does it have to be in order to not clip so much of our precious laser light in the arm cavity. So if the round trip loss is something like 50 ppm, then of course we don't want to allow more than 1 ppm loss, better less. So something like 3 for the ratio of aperture radius to beam radius seems the minimum we could accept.
So you're just doing this for gravitational wave detectors because we have them, but shouldn't you make it shorter so you have smaller beams? And you don't gain anything by making it 4 kilometers long, do you?
You do, because you gain displacement sensitivity.
Wait, you're going to have a magnet the whole 4 kilometers?
You don't need it, but if you have it, I mean, it's principle there's this distinction to prototypes or any dedicated experiment, but it's hard. First of all, to get 10
I know, yeah.
You know, and you need probably large beams.
But it's just that if you make it really big, you're going to have big beams. There's no way you can make it both long and have small beams.
That's one of the advantages, and you don't need the lens, but it doesn't harm either. Yeah, you need displacement sensitivity. Okay. And so if we take 3 beam radii, this is what I have been using for the example cases. So here we have beam weights of 9 millimeter per 10 by 12 around the middle of the beam tube, where the beam weight is, except for geo. Then 3 times this, and then some margin to have an additional beam tube and some aperture and so on. So what I used as an example case is 55 millimeter radius, so 110 millimeter diameter aperture. And I started to calculate, can it be done with a simple linear magnet? So this is to have a perpendicular field on your beam axis is the same problem as in particle colliders. So where you want a vertical field such that the Lorentz force would pull the moving particles toward the center. So in principle, this is a well-known problem for particle accelerators. And so we would have a current running next to the tube on one side and back on the other side and get then a vertical field here. And in a cross-section, it looks like this. So the tube in the middle and the two conductor cross-sections on the outer side. This is exactly what the particle accelerators do. They do it with superconductors and in a slightly optimized shape and so on, but superconductors are not so suitable here, at least not for amplitude modulation, because they can only do very small amplitude modulation. So
You need a yoke to return the field.
Yeah, I'll come to that.
And
So-
all the thing together.
No, okay, but you can make some strong structure around it, and you can calculate when it will fly out.
There's
So-
piles of them sitting in the mushrooms in Texas. The super collider made loads and loads of these things. And they're sitting there collecting mushrooms.
Yeah.
You were there.
I was there. I even wrote proposals.
Okay, so you
I
find
those
when taking the simple conductor, you find a simple scaling law. So the excitation, the B squared times D, is proportional only to the power, to the electrical power you dump into the system and to some geometry parameter. So given that you have some material as copper for the conductor, which is the best material at room temperature. So it all depends on the electrical power you put into it. And so I calculated a linear magnet like this for only 1 Tesla square meter, which is really at the low end. The thermal dissipation from this would be 300 kilowatts, just copper losses, not so nice. But the reactive power is almost 10 times this because it's an inductor, and so there's really a lot of energy in the B field, and that means it has 2.5 megawatts of reactive power. And if you put some ferromagnetic material around it, this goes down to 1 megawatt. So it doesn't have very much, it only gives you a factor of 0.5. And the electricity for this would cost in Europe 2 million euros to run it for 1 year. You have, I think your electricity costs only half here, but it should be more expensive. That's too cheap. So the next step is to do intermittent operation of a magnet. So with the same magnet, you drive with a sine wave and take 2 megawatts to have a SMR 1 in 1 year or something like this. You can do more clever in principle, by run it with double the power for 1 minute, say, and then have 1 minute break. Because then in this 1 minute where you run it, you have double the signal and 1/4 the integration time, but you have a break of equal length, so that brings your integration time overall down by a factor of 2. And this is as I said earlier, the basic motivation to go to shorter and shorter pulses, because overall it brings your integration time down, or for the same integration time, it brings your power down. So with this operation...
Shorter pulses of the magnet,
Hmm?
of the magnetic field, not the laser beam.
Yes, right. The laser beam is continuously below. So with this same example I calculated earlier, for 2.5 megawatts, we could bring down to 20 kilowatts, which is more reasonable in kind of intermittent operation. But the pulses now would be something like 100 megawatt pulse over 10 milliseconds, which is 1 megajoule of energy. That's not so crazy for pulse magnets. It starts to get ambitious there, with what the people told me, but it's still kind of standard once you have designed a magnet. It doesn't exist yet, but 1 megajoule corresponds to 240 grams of TNT exploding. So, and you would have to do this every 50 seconds and 600,000 times. Yeah, okay. So, okay, I would agree with you that this is not so feasible.
It's not, you can engineer it, but it's a challenge.
So electromagnets are difficult because of the high energy in the B field, which you have to get in and out, which makes all this reactive power. And similarly for pulse magnets, you win in the average energy, but on the other hand, they are much harder to engineer because, as you said, the forces are much higher if you go to pulse operation. And so this is one of the big problems in making pulse magnets, the forces they try to put in the car. And so the other idea is to look into what PVLAS did to use permanent magnets, which has the big advantage that the field energy does not have to be shifted around in and out. It's just permanently there since the magnet has been constructed. And so the idea there is similarly as the PVLAS magnet, which is built like this. So you have a cylinder out of neodymium iron ore, so the best material for permanent magnets with the strongest permanent magnetization, and the laser beam goes within a central opening. And then the arrows here in the cross-section denote the orientations of the magnetic domains within this, and so this is a kind of clever array, which then in a superposition of all these fields, you get just a parallel field in the middle. And with this, you can get a field in the center of the tube, which is even larger than the remnant magnetization of the material, which I find quite surprising somehow.
The Faraday isolators are the same?
No. On the Faraday isolator, the magnetic field is along the axis. But in principle, they are constructed according to similar ideas, but you have to have the magnetic field on the axis.
They play the same trick with the
Yeah, you can.
With
the
the
vector character of the.
Right. And I recall assembling these things is not so easy.
Yeah, but this is done by a company for you.
What's the strongest magnet?
Well, the material does about 1.35 Tesla, 1.4 Tesla. That's the maximum you can get for the material. But PVLAS has a magnet like this, which has 2.5 Tesla on the axis, just by linear superposition. So that works very nicely. And so I calculated a magnet for this, for example, with this our diameter that we want, 110 millimeter diameter. This would cost $50,000, so not so expensive, and weigh 328 kilograms, so it's not something like this.
And the forces that want to tear it apart?
On what?
You have to hold the thing together, otherwise it's
Yeah, but it's,
blows apart.
the PVLAS magnets are very similar. They just have a smaller central opening, but they weigh 400 kilograms and have 2.5 Tesla in the center. So it's not crazy. We are asking the company at the moment. And so you would spin this magnet around a tube with 25 hertz with magnetic bearings, for example, and that would give you a spatial modulation. But there's also an idea, and this is a patent drawing even, that you can have two nested cylinders which you rotate against each other, and then in effect you can get an amplitude modulation which doesn't change the direction in the middle. That certainly would be a bit harder, so that would be advanced QPD measurement. That's a side note. And okay, just one more thought then about how to really implement this. So the biggest concern would be, in some sense, systematic errors. So I think, of course, one needs gate valves, ideally, on these beam tubes, and then two chambers which carry suspended baffles with a central opening, which is a little bit smaller than what you want to have for your interaction region. And then a small tube inside, like a ceramic or glass tube, non-conducting, and then the interaction region with rotating magnets or modulated magnets, and if needed, some protective vacuum chamber around. Okay, and so where can we do it? So as I said, in GEO, this would be a hypothetical upgrade. This is our sensitivity as of today in displacement, 10 to minus 19 meters per square hertz. And this would be an upgrade targeted at displacement sensitivity. And yeah, as we said, it's hard with small beams. The beams are only 1 centimeter large at the central station in radius in GEO. And LIGO, as you know today, is already here. And so, yeah, we we already discussed it. Displacement noise is hard to reach with small beams, but maybe there's a way. So this is Virgo. Virgo has middle stations, but unfortunately no gate bulbs in the middle stations. Very sad. But Hanford has middle stations and gate bulbs in the middle stations, so it's the only detector that has this. So it's a little bit busy, but here are gate bulbs, and between those gate bulbs you have about 10 meters of detection region. So it would be a little bit tight, but you would have a chamber here and a chamber here, and then leave something like 6 meters of interaction region. And yeah, I think it could be installed during an A+, in the second phase of the A+ upgrade, something like 2 or 3 years from now, or in the way. And okay, worst case, worst case, if it doesn't make noise for the gravitational wave detector, you have to take it out again. I think that's the basic risk. But I think it's not probably anything. Okay, last slide, second to last slide. Of course, many calibrators have been predicted in the past, and they are not all useful. But if you turn the problem around, you could say QED is so well tested and has so beautiful predictions that you can make a QED calibrator out of this with only one parameter, which is your excitation field. And this one parameter, of course, the permanent magnets are very stable, and also they can be measured very well. So this can easily go to a 1% level, and of course, as sensitivity increases, we know that at some point we want to have calibration at the 1% level. And of course, it still needs long integration time to get to this level, but as the detectors get more sensitive, you kind of get this for free as well. So I think it would be possible to get in the percent region at some point. Okay. So vacuum QED at gravitational wave interferometers. It's a different method. So far, it measures the phase-lag signal rather than polarization, what the other experiments are doing. It is ambitious, but it kind of looks feasible to me. It's not totally crazy. And it's a quasi-parasitic addition to an existing facility with not too high risk, I would think. And permanent magnets seem to be an option for now. Okay, thank you.
Have you thought about how to distinguish between the gravitational wave signal that might be there, a continuous gravitational wave?
I think it's
Of course, it won't be
no
continuous
problem
wave
because
modulated.
you can perfectly measure your excitation signal. You have all sensors there, and you exactly know what there should be. So you can perfectly search for it and perfectly subtract it as well. But it's such a small signal. It's like a very small pulsar in the noise.
Don't put it right where a pulsar is.
Okay.
Of course,
Continuous
continuous waves are modulated by Earth's motion, and it cannot be.
But you have total control. It doesn't need to be
Exactly.
regulated.
I don't want to put it in one detector.
I don't know. I wouldn't see any problem there.
Do the beam tubes help you? Since you're modulating this field in some way. Stainless steel beam tubes that are tracking twice the system.
If you leave it as steel, then it takes away 50% of the effect, and if you put a lot of energy also, then you heat the tube. So
It doesn't help you, but the good news is it doesn't crush your body.
because it's far away from the Yeah, of course. I mean, that's a nice thing here, because that you are kilometers away from mirrors. So the only systematic, but the systematic errors you're facing is scattered light. Things like this.
I think the magnetic field will cause this kind of magneto restriction in the future, so the beam tube will modulate because it will modulate.
Sure.
And the scattered light field will get modulated.
Yeah, but that's in principle why there should be baffles at the entry and exit of the beam tubes. But of course, you have to take care of systematic effects. It's the same as for the other experiment. In principle, yes, but you might try to mitigate this by baffles, for example.
Or putting some numbers on the tube.
yeah, on the tube and on the battery suspension. And,
Is there any residual problem from the vacuum itself? Not, I mean, what the molecules that are left is this gigantic varying magnetic field.
yeah, it is. So there's the Cotton-Newton effect in gas, and so you have to know the gas composition. But at the level of we have normally tubes or should have, it's just okay. But on top of that, you have to monitor the gas composition.
And is there anything similar to this birefringence effect that looks like the Faraday effect in vacuum?
Faraday effect in vacuum.
That is, so counter-propagating beams would see different shifts,
Faraday effect is purely classical.
but there's no equivalent in.
This is purely quantum.
I don't think so.
Yeah, I'm just asking. You can't find any term at the same order in QED that has something that looks like that.
Not that I know.
Any QD effect would be code detect. It's not a
So what's for your Hanford mid-station design, what did you estimate the Tesla squared meter value when we were looking?
Game it's something like 10 with either 2 or 4 magnets. So magnets with 1.6 Tesla in the center over 4 meters or something like this, and then integration time with the design sensitivity is of the order of 1 month, but then it gets better with upgrades. And so you can build up some reasonable SNR.
Does it get better if you do the shot noise scrambling technique with 2 photodetectors?
You should tell me later.
Does this effect have any relevance for astrophysical sources with really large magnetic fields like pulsars?
Yes. So for astrophysics, there are proposals and ideas also, of course, how you can use strong magnetic fields of pulsars or neutron stars or magnetars even. So, and there's a similar effect to gravitational lensing, which is birefringent lensing. So if you have of course you have a gradient across the star, and if the light comes, it can be bent. Just very similar. This is just there's a satellite, I think, dedicated to the polarization of X-rays, which is looking for this effect, which started around the end of last year. So it's a direction where people think also.
This modulation is in the middle of the tube, not at the end, so it seems like you can distinguish between the displacement noise, phase shifts which come at the end, phase shifts which are in the middle of this. Like the displacement noise screen technique allows you to be sensitive to different places within the cavity.
I don't know, for what does it help?
Well, the displacement noise idea is that if you look at multiple data streams from Earth, you can basically you do close subtraction. You can do it online, but you can cancel out